My name is Rajesh Lakan. Oh, it has one new person. Oh my god. Rajesh, R-A-J-E-S-H Lakan. Right, and I think that's all you're going to get. Nice. So, introduction to abstract algebra. So, we want to introduce abstract algebra. So, we'll start with concrete and then we'll go. You all remember functions? Yes. You all remember one-to-one and one-to? One-to-one, y'all. A function f is one-to-one if and only if what? F of A equals to F of B implies A equals to B, yes? Everybody's okay with this? Yeah. Perfect. Determine whether F of X equals to 2x plus 1 is one-to-one where F goes from Q to Q. Q is the set of rational numbers. 2 minutes. This is important, where A and B are in the domain of F, right? This is very, very, very important, right? Alright, so proof. So first things first, we need to take two elements from our domain, right? Our domain is Q. So let me X or Y or A or B. Which one do you want to use? X, Y. So let X and Y be elements of Q. Now this Q is the domain, yes? Assume that Fx equal to Fy. What is our last line here, y'all? What is my last line? X equal to Y, yes? Good. Everybody's okay with this? And now we just fill in here. That's all. We just fill it in. Simple. F of x is 2x plus 1 equals to 2y plus 1. And it's a proof, right? So all those very baby steps, just give us it, right? Just give us it. Which would imply that 2x equals to 2y, obviously minus 1. And this would imply x equal to y. Everybody's fine? And we put our box. Yes? Perfect. Next question. We have our function g of x such that g goes from r to r plus. And g of x is e to the 2x. So the question is the same. Prove that g is 1 to 1. Same procedure. We take two elements in our domain, which is r, a and b. And we want to assume that f of a equals to f of b, and do some working and show that we get a equals to b. So take a few minutes, pause the video, work it out. When you finish, press play. So we get f of a e to the a minus 2, which is e to the b minus 2, which implies that a minus 2 is b minus 2. Therefore, we get a equal to b. So you all understand? Perfect. So now let's just go into the question on the text. So we want to prove that if we have two functions, f and g, and both are injective, we want to prove that g composition f is injective as well. So if we have f goes from a to b, g goes from b to c, and then g composition f will go from a to c. So if I want to show that given that f and g are one-to-one or injective, I want to show that g composition f is injective. What is the first thing I have to do? Well, proof. I have to take two elements in my domain. So the domain of this function is what? So remember, we take an x in f and we get f of x, and that value goes into g. So my x value will come from f, which is a. The domain is a, yes? So let x and y be elements of a. Now I want to assume that the function f of the function, g composition f of x equals to g composition f of y, and then I want to show x equal to y. Yes? So we start. So assume that g composition f of x equals to g composition f of y. And my goal is to show that x equal to y. Great. So let's go. So this is g of f of x equals to g of f of y. Everybody sees that? Great. Now, I know since g is one-to-one, remember g being one-to-one, if g is one-to-one, then g of alpha equals to g of beta implies that alpha equals to beta, yes? So in this case here, since g is one-to-one, g of this here is my alpha equals to g of this is my beta. Therefore, I can write that f of x equals to f of y. Lovely. So we get f of x equals to f of y. And we will justify since g is one-to-one. So now we have f of x equals to f of y. Can anybody see what is our next line? X equals to y, yes? Yeah. Why? Because f is one-to-one, which implies that x equals to y since f is one-to-one. Hence, our function, which is g composition f of x, is one-to-one. Everybody's okay? Now notice we do not know what f is, we do not know what g is, we do not know what g composition f is. But we know that if we have two functions that are injective or one-to-one, then the composition of those two functions will also be injective. So let's apply this. If I have another function, let's just create this h function. So I have h such that you're going from q to r plus such that h of x equals to 2x minus 1. So this is my question. Is h one-to-one? Is h one-to-one? And the answer is yes. So we could proceed with our normal steps. Take two elements in h. F of a equal to f of b. therefore A equal to B, therefore H is 1 to 1. Or, I don't know if you all can see this, H here is actually G composition F. So, F is this and G is this. So, E, where X is I put F. So, it's E to the F of X minus 2. Which is E and F of X is 2x plus 1 minus 2. Which is E to the 2x minus 1. Yes? So what this says is, if you, let's just say you're a teacher or a lecturer, and you want to create basic questions, you just need 2 or 3 functions that are one-to-one and compose them, and compose them, and compose them. And you get a whole list of questions that you know will be one-to-one. Everybody follows? So just to re-emphasize the point, the only thing you need to make sure is that the domain and the codomain are correct. Because you're going from one function to the next. And that is the only thing that may cause a problem. So G composition G would be what? G is E. So E to the Gx minus 2. So this is E to the Gx minus 2. But Gx is E to the x minus 2. You see that? But if you see a question like this, is a horrible question. Determine whether or not this function, called M, which is really G composition G, is one-to-one. I mean, if you see this, whoa, what is going on there? Confused. And if I want to be really ridiculous, I could compose this with F, or G, or H, or K, or it doesn't matter. Or I could define an x function P of x, which is sine x, x less than pi on 2, because I know this is one-to-one. And then compose this with any of those. We all follow the point, right? So this is the power of abstract algebra. You do something abstractly, and you prove it, and therefore you know it will hold for everything else. So now, I just want to remind you all of the proof of how to show something is onto. So let me just show G is onto. So remember, G is onto if for all y in the codomain, in this case the codomain is R plus, there exists an x in the domain, which is R, such that G is my function, G of x equals to y. So G of x equal to y gives e to the e to the x minus 2 equals to y, which implies that x minus 2 equals to ln y, which implies x equals to ln y plus 2. Now a couple of things here that we need to be certain of. We need to ensure that this x is in my domain. Will ln y always exist? So ln y does not exist for y equal to 0 or less than 0. But our restriction in our codomain is R plus, which means ln y will always exist. So this will be a real number, and ln y plus 2 will also be a real number. Therefore, this will be an element of my domain. Therefore, and this will happen for all y. Therefore, G is onto. Everybody's okay? Now, please pay attention to these things, because when we deal with homomorphisms and isomorphisms, it comes back. So although it is a revision, it is very important because you will meet it in a couple lectures down. Yes? So I leave the other two functions, f and h, for you all to prove that it's one-to-one. So now we're actually going to get into groups, which is where the meat of the matter lies, and the entire course from here on will be based on groups and further systems that we create. So definition 1.1, a non-empty set. So that's the first point. The first point, we must have a set and it must be non-empty. So point number 1, non-empty. So a non-empty set G is said to form a group if associated with G is a binary operation. Generally binary, we assume it's closed. an operation could be closed or not, but if we say a binary operation, that means that the operation is closed. Called product and denoted by dot such that 1 closure happens. So the first point is just ensuring that G is closed on the dot. So for the group we write G comma dot is a group. So let's deal with the first point, closure. So for a set to be closed, it means that if we take elements in our set, the output has to also be in our set. So for example, if I were to take A and B in Z, and my operation, my binary operation, A star B is A plus B over 2. Is Z closed under the operation star? The answer is no. Why? Z only consists of whole numbers, positive, negatives, and 0. Positive, negative, and 0. Whereas if I take two elements, any two elements, say 1 star 2, I get 1 plus 2 over 2, which is 3 over 2, which is not in Z. You all follow? So Z is not closed on the star or asterisk. However, if instead of having Z, our set was R, then for sure star would be closed in R. You all follow? Sorry, the set would be closed under the operation, because 3 over 2 is in fact in R. So we took two elements in R and we got our answer in R, therefore it's closed. However, with this one we took two elements that are in Z, but our output 3 on 2 is not in Z. Yes? So it's analogous to having a room. So let's just say we have this room and we have humans in the room, boys and girls, and we lock both doors. And we came back 3 hours later and somehow we managed to see a dog. I mean, that's crazy, right? I mean, somehow the room, which is analogous to the set, was not closed. So a door was open and a dog walked in. Do you all follow? Yeah. So just remember that if you're having some problems to understand closure. So the next point is associativity. So associativity means more or less the order of the brackets doesn't matter. So if I have A plus B plus C, this is the same as if I have A plus B plus C or A plus B plus C. You all follow? So not all operations are associative. So we need to ensure that the operation is associative. So for example, take a few minutes and determine whether this operation A star B equals to mod A minus B, where A and B are in Z. Determine whether this is associative. So we would need 3 elements, A, B, and C in Z, and we'd have to determine A star B star C, determine what this is, and then determine A star B star C and determine what this is and ensure that both are equal. And if they are not equal, for all elements, it has to be for all A, B, and C. If you were to get some specific combination of A, B, and C that it works for, that doesn't make a difference because it has to work for all elements. So finishing off, if this is equal to this, then it is associative. If it is not, then it's not associative and you only need to give a counterexample. So you can pause the video, take a few minutes and work on it yourself and press play when you're ready for the answer. So it is not associative and it's much easier to choose specific values for A, B, and C, work out this side and work out this side and show that you do not get the same answer. Everybody's okay? Nice. Great. Identity. So our next condition is that there must exist an identity element. So I'll start with the real number system. So an identity element is an element E such that A star E equals the element itself, A. So this is the definition of an identity element. So for addition, our identity element is, so we want an element A star E, A plus E equals to A. So E is 0. You all follow? So A plus 0 equals to A. And because E is to the right of A, E is called the right identity. If it were to the left, it would be called the left identity. And if we have a left and a right identity, then we call it D identity. Everybody's okay? Nice. For multiplication, it's the same thing. So A, E equals to A. What is my identity for multiplication? E is 1. Everybody's okay? And it works both left and right. So after we have identity elements, then we could speak about inverses. So an inverse is an element such that A star, A inverse gives me the identity. So it makes sense that we could only speak about inverses after we have the identity, because this uses the identity. So for addition, A, our operation is plus some element A inverse equals to 0. This gives A inverse is negative A. Do you all follow? So when my operation is addition, this reads that the inverse of A is negative A with respect to addition. When my operation is multiplication, it goes A star A inverse equals to E, which is 1. Therefore, A inverse is 1 over A. Yes? Now this makes more sense, right? When you have 4 to the minus 1, it's a quarter. But that is only for multiplication. So we have inverses. And these two things, this must happen for all my elements as well. There must be no elements in the set G that does not have an inverse. Yes? Great. Before we move on, I just want to make one point. With respect to associativity, being associative and commutative, both properties are more or less disjoint. So in other words, you can have an operation that is associative and not commutative, and one is commutative and not associative. Or you can have operations as both commutative and associative, and I assume you could have operations as just neither. Yeah? So this here would be commutative but not associative, and anybody could think of an operation or system that is not commutative but it is associative. Not commutative but it is associative. Matrix multiplication. So matrix multiplication is not commutative in that AB is not equal to BA. So not commutative, but we know A, B, C equals to A by B by C. You all follow? Great. So we move on to the note. We say that G comma dot or G comma star or G comma asterisk is a group. And we generally write G is a group and take the operation to be dot. So instead of writing all the time that G is a group or G comma dot is a group or G comma star, we understand we're doing with group theory, and generally you call a group G because it makes sense. So we could just represent G as a group. Yes? Also note normal rules for A to the n. So if our operation is addition, then A to the n would be A plus A plus A plus A n times, which is straightforward. 1 or E may be used to denote the identity element in groups. So coming down in further sessions, we might use 1 or E. It depends on the system. We may also write, so if it's under multiplication, instead of continuously writing our operation between elements, we could just leave it out and it's understood. So instead of writing A by B, sometimes you might just write AB and you would know that is A by B. or A the operation by B. Now this is a big point. So clearly all groups must have at least one element. Anybody cares to give a guess what that element may be? The identity element, yes, very good. And it being the identity element will satisfy all the properties. It will be non-empty because it has the identity element. It would be closed. The identity star the identity is the identity. It would be associative because you only have the identity. It would have an inverse. The inverse of the identity is the identity. So it will satisfy all the properties. We're moving on to definition 1.2. A group G is said to be abelian or commutative if the binary operation is commutative. So this is important. Remember, in our definition of a group, our binary operation only needs to be associative, not commutative. But if we have an operation which is commutative, we call it an abelian group. Yes? Great. Now these are things you all would have encountered before. It's just to make sure you all know and we are on the same level before we really get into some interesting stuff. Definition 1.3, the number of elements in G is called the order of a group and is denoted by two vertical lines G. So the number of elements in a group is called the order of a group and is denoted by the order of a group called G. A group is said to be finite if G is finite and infinite if the order of G is infinite. Makes sense, but we still need to define it. So we have a few examples of groups here. The set of all integers is an abelian group under addition. So the set of all integers, so Z, you remember Z is ... -2, -1, 0, 1, 2, ... So this group with addition is a group under addition. So let's see, is it closed under addition in that if we add two elements in Z, do we get another element in Z? Yes. 100 plus a million is 100 and a million. You know, I have to give a little joke, right? I have to give a little joke. So 5 plus 3 is 8 and 8 is in Z. And so that's close. Is it associative? Yes. The order doesn't matter. If we add elements, it's the same. We're going to get identity. What would be the identity? We've gone through this already, 0. And the inverses would be the negative signs. So the inverse of 2 would be -2 because when you add 2 plus -2, you get 0. Nice. So the second example, so example 1.4.2, the set of all rational numbers is an abelian group under addition. It's more or less the same thing. Example 3 as well, but I want to go into example 4, which says this group G. Now you all know I love complex numbers. Complex numbers is the best thing in the world. So we have this set, and we claim that this is a group where we have our usual multiplication. Yes, so I wouldn't write, so normally you wouldn't have equal to here, so I would either write this as the group, or I would just write G comma as the group, or I could just write G. Everybody's fine? But this is just to make sure you all know what the set is. Perfect. So let's just make sure this is a group. What would be the identity element for this group? 1. Yes? What would be the... Okay, so 1 is here, so it's non-empty. Is it closed? So for closure, we need to ensure that if we take any two elements, then the product is also in G. Now when we have finite groups, something that is very, very useful is a group table, a multiplication table. So we have multiply, and we have 1 minus 1, I minus I, 1 minus 1, I minus I. And this is a neat way of determining whether the group is closed. So, sorry, yes. So remember, it's row by column. So 1 by 1 is 1. Now because 1 is the identity, I can just rewrite these things. So this is going to be minus 1, I minus I. And because 1 is here, I can rewrite this entire row. Yes? So minus 1 by minus 1 is plus 1. Minus 1 by I is minus I. Minus 1 by minus I is I. Now, a few things to note in this table. If it's a group, then there will be no repeats in a row or a column, which is a major point. So we'll use it in a while. So I by minus 1 is minus I by I is minus 1, and I by minus I is 1. So we have minus I now, so minus I by minus 1 is I, minus I by I is 1, and minus I by minus I squared is minus 1. Yes? So if we look in, so this is my table here, right? So 1 is never repeated here again, nor is repeated here again. Minus 1 is never repeated here again or here again. I is never repeated here again or here. Minus I is never repeated here or here, and it's the exact same for all. This comes in very handy if you were given a group and elements were missing. You could fill them out like plain, like Sudoku. Right? I have never figured out one of those yet, you know. Even the easy ones. Well done, you have to teach me. So what would be the order of this group? So the G, what would be the order of the group? The order of the group G is the number of elements in G, which would be 1, 2, 3, 4. Yes. So the order of the group would be 4. I'm a bit excited, so I just want to bring to your attention a theorem that says if we have a finite group, then the order, with order n, any element raised to that power gives you the identity element. Yeah. So in other words, if I would have 1 raised to the power of 4, this gives me the identity, which is 1. Minus 1 raised to the power of 4, this should give me 1 as well. I raised to the power of 4 is 1, and minus I raised to the power of 4 is also 1. Y'all okay? Nice, perfect. So, example 6. G consists of real numbers 1 and minus 1 and a multiplication of real numbers. Question, is G a group? Yes or no? Oh, this is a nice question. So if I have G as 1 and minus 1 under multiplication, is this a group? Yes or no? Yes? It satisfies everything? If it were under addition, would it be a group? Why not? 1 is the identity. Oh no, the identity not there. Very good. 0 would be the identity and 0 is not there. Okay, so assume we had the identity then, right? Any other contradictions we would get? No. Yes, no inverse. But I was hoping you all would see it might not be closed. Because 1 plus 1 is 2. Yeah? And yes, yes. Lovely. Okay, so what about this? If we have I and 1 with multiply, will this be a group? You all understand this thing very well, boy. My God. No, okay, okay. I mean, you're making this really nice. So why would this not be a group? The identity is 1. Look, the identity is 1 here. So it's not closed, right? So again, if you want, you can draw the table I and 1, and I and 1. I by I is minus 1. 1. This is I, and this is 1. But minus 1 is not in there. You see it? That's the power of the table. You'd have to look and figure it out. What about I and minus I then? What about I and minus I? So we are with multiplication and we have I and minus I. Will this be a group? Reason? It has no identity. Yes, that's correct. I don't want to steal it. Yes, so this doesn't have an identity because 1 is the identity for multiplication, as well as it is not closed. So again, you could draw the table if you want I minus I minus I by 1 is minus 1 is not in here. Straightforward, very quickly. Point 7, the set of all 2 by 2 matrices is an abelian group under addition. So the operation is very important. We are in addition here. Nice. So we have a few more examples just to ensure that you all fully understand what a group is. So is n with addition a group? N plus. Is this a group? Yes, no. No. So n would have 0, 1, 2, dot, dot, dot. Why is it not a group? Because it has no inverses. Because the inverse of 3 would be negative 3, but negative 3 is not in n. So it is not a group. Alright, so then if that's so, is Z with plus a group? Yes, yes. Alright, so is Z with multiply a group then? I feel you all did this before, you know. So you all hit the nail on the head. It is not a group. Anybody cares to tell me why? Because 0 is its Z, and the inverse of 0 will be 1 over 0, which is not possible. It's undefined. So very good, very good. I must say, you all are surprising me. Yes? Right, so now we are on handout example 1, which is our matrices handout. This is a bit more involved. So let G be a set of all 2 by 2 matrices, A, B, C, D, where A, B, C, D are real numbers such that AD minus BC is not equal to 0. So meaning that the determinant is not equal to 0. For the operation G, we use multiplication, so it's standard multiplication. Now we want to show that this is a group. So the first thing we need to go through all our properties. So the working there simply multiplies, which means we're looking for closure. So we multiply 2 matrices, it's in there, and we get this big matrix, AW plus BY, AX plus BZ, CW plus DY, and CX plus DZ. And then we have to show that two things, that all those numbers are real, because it's a set of 2 by 2 matrices in which A, B, C, and they are real numbers. So since R is closed on addition and multiplication, AW plus BY would also be a real number. It would be the same for all of those. The second point is to show that it satisfies the property that AD minus BC is not equal to 0. Now in this case here, so in this case we have AW plus BY, AX plus BZ, CW plus DY, CX plus DZ. So in this case, this here would be my A element, this here would be my B element, this here would be my C element, and this would be my D element. So when the question says AD minus BC is not equal to 0, it's this multiplied by this, subtracted from my B element, which is this, minus this, and then I have to show that that is non-zero. You all follow what's going on? Nice. So the working is there as well as the justification. So I'll leave that for you all to do. Once we've ensured that that happens, then that means that G is closed under matrix multiplication. Next we take the associative law. Now that holds for matrices. And we have the identity element. So I is 1, 0, 0, 1. That satisfies the AD minus BC is non-zero. So it is in the set, which means it's non-empty. The working going down there, we are getting into inverses. So it's, I wouldn't say it's cumbersome, it's just algebra. So I would leave you all to go through that on your own time. And so we've come up with the inverse, and then it shows that if you multiply on the left and on the right, you still get the identity, which means left inverse, right inverse, therefore the inverse. And we conclude. So therefore, in short, G is a group. Anybody has any questions? Perfect. Right, so we just have a few more pages before we go on the break. So I must say you all are doing very well. I love the enthusiasm and the energy. So we are on lemma 1.5. Let an element X of a group have, an element X of a group G has exactly one inverse X inverse. So this is a very important method. So this method would be how you prove that something is unique, which is big in mathematics. And the method is the same. So if you want to show that one of something exists, you assume that there are two, and show that those two are equal. Because if you can show that two are equal, then it means you can continue the process. So in other words, if I say I have E, and I have E1 and E2, 1, E3, go on, and I want to show that there's only one E, so let's just say E, then I prove that E is equal to E1, where the properties of E1, E2, E3, and everything else are the same. So if I can prove that E is equal to E1, then that just means that we just have E1, E only, and then E2. But because I've chosen E1 and the proof for E1 use no special property that E2 and E3 does not have, so in other words they all satisfy the fact that some special property, whatever it is, then that also means that we can use the same proof for E2 and for E3 and for En. You all follow? Therefore all of them will be equal. So therefore there's only one identity element. So, there's only one whatever it is we're speaking about. And this would hold across mathematics. It doesn't matter which area you're in. If you want to prove uniqueness, this is generally a standard method. I mean, obviously, depending on the field, it might be different. I mean, I don't know all the fields in mathematics, so I can't speak in that general term. Alright, y'all, so we would like to continue with this proof. Lemma 1.5, an element X of a group G has exactly one inverse. So, We know from the axiom that we know that a group contains at least one element which satisfies the property. So a group must have an identity element. So there would be an element X such that X by X inverse is E. We understand this. Now we want to show that if there's another element that acts as an inverse, then both elements are the same. So we let Z be another inverse. So if Z is a right inverse, then X by Z equals to E. Remember, X is my element, and if Z is an inverse of X on the right, then an element by its inverse gives me the identity, yes? And our goal now is to show that Z is equal to X inverse. You all follow? Nice. So the proof is in the text. So we know Z is E by Z, but we could rewrite E as X inverse X. So we get Z. And we know, because it's a group, then multiplication is associative. So the order of the brackets does not matter. So we can change the brackets. So we get X inverse by XZ. But we've now assumed that XZ is E, right? Remember, XZ is equal to E. So we get this is X inverse by E. And anything by E is anything. So we get X inverse. So therefore Z is equal to X inverse. You all follow? And the property we used was the property of an inverse, meaning that an element times its inverse is equal to the identity. That's all we use. So if we were to use the next element, it would be the exact same working. That's a very good question. Now, yes, we have to show right and left inverse because, yeah, I know. Just take a minute and do it, you'll get full marks. So the second part says similarly, if W is an element of G which satisfies that which is the left inverse, then W equal to X inverse. So I'll leave that for you all to do because I know it's been a while since you all have attempted anything. So please take a minute or two and pause the video and attempt. When we get back, we would not go through the solution. Lemma 1.6. Let X and Y be elements of a group G. Then the inverse of X, Y. You all look at this. This is important. This is how you read it. The inverse of X, Y is Y inverse X inverse. So this is a proof, this is a standard proof in which you encounter. So if you want to show that something is the inverse of this is that, there's a method. Now I was taught this method by Jay, who hosted the first study group, to my knowledge. So if you want to show that the inverse of this is that, then you do two things. The first is you multiply this by that, and you show you get the identity. And the second thing is you multiply that by this, and you show you get the identity. Anybody knows why it must be done on both sides? Very good. Because we're not sure if it's coming to shake hand, shake hand.
I mean, it would be easier to do it.
You all understand, right? Great. Now, if you don't like this notation, I mean, I personally like it because, it brings in English into it. If you like to be all mathematical, then if you want to show the inverse of alpha equals to beta, then what would you show? Alpha beta equals to E. So remember, this would be working at dot 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 E. And then beta alpha dot 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 E. You all follow? So if you're not comfortable with this one, use this one. It doesn't make a difference. So let me go through this proof with you all. So we're proving this. So proof. So now we start. Let's just do this one, right? So this would be equivalent to saying that xy by y inverse x inverse equals to, and we want to show that we get the identity. So this gives x by y, y inverse, x inverse, and since a group is associative, we could regroup the brackets. Sorry, we're not dealing with a group. Yes, we're dealing with a group. So we could group x by y inverse. And this gives the identity element. So this gives x by e, which gives x by x inverse, which gives e. You all follow? Nice. Also, don't just write the next line, huh? Give us some sort of idea that we know what you all are doing. So also now we switch them. So this here would be, so we've now shown that this by that equals to e. So now we want to show that by this equals to e. So we want to show that y inverse x inverse by xy equals to e. So this gives, it's more or less similar, y inverse by x inverse by x, y, and then the x and the x inverse with the x will give you e. So you get y inverse e by y, which gives y inverse by y, which gives e. Do you follow? So hence, and then you conclude, hence the inverse of xy equals to y inverse x inverse. You must conclude with your box because you want to get full marks. Lovely. So please attempt this question on your own time, just to ensure complete understanding. So we want to show, assuming matrices, that the inverse of A, B, C is equal to C inverse, B inverse, A inverse. I think you all are seeing it, right? So the baby steps, well, the general format would be A, B, C by C inverse, B inverse, A inverse, working to get the identity, but the identity for matrices would be I. Yeah. It is 1, 0, 0, 1 going down, but we don't know if it's two-dimensional matrices or 3 or 4 or 5. So we write I. Yes? And the second point would be, we reverse them, C inverse by B inverse by A inverse by A, B, C equals to I. Yes? Nice, I like it. Shake heads. You're making me feel good now. Or I should say better. So, we have theorem 1.7. Let G be a group and A, B, and C be elements of G. If either A, B equals to C or B, A equals to C, then B equals to C. So, for this proof, we have to do both cases because it's an OR. So, in other words, if I'm standing in this room, I can go downstairs or I can exit this room by either going through my door to the left, or the door to the right. Which means that in order to prove that statement, I have to go through the door to the left. So I have to show it works for the left. And then show that it can work through the door on the right hand side. You follow? I can't only do one side because then it doesn't make sense. It's not a complete proof. Lovely. So we're following on the paper for this one because it's more or less straightforward. So I have AB equals to AC. So remember what we want to show. We want to show the then part. Just to briefly go over that. I don't know if you all would remember. So we want to show that if AB equals to AC or BA equals to CA, then B equals to C. So in other words, this here is my P and this is my Q. So remember, we assume P and then show Q. That's the general format. But because this is our OR, so we'd have case 1, which would be if AB equals to AC, and then we show that V equals to C, and then case 2, case 2 would be if BA equals to CA, and then we have to show B equals to C. Yes? And then we conclude. So it's there. So first we start with what we're given, which is, so we suppose that AB equals to AC. And then what we did, we multiplied by A inverse on the left hand side. And we regrouped our elements A with A inverse because it's a grouper and it's associative. A by A inverse gives me E. So our next line gives E by B equals to E by C, which implies that B equals to C. Everybody's okay? Anybody has any questions? It's perfect. So we want to start with the next line now. So we assume if BA equals to CA, then we show B equals to C. So I leave that for you all to do. Simple, straightforward. Please attempt these questions, because as the study group goes along, the method of thinking would require thought processes like this. Perfect. So now we are on subgroups. So we have a group. So we have a group G, and we have a subgroup H. So more or less a subgroup of a group is a set from a set that is also a group. So in other words, I have a set G, and instead of taking all the elements in G, I just take some of the elements in G, I call it H, but the elements in H also form a group. So therefore, H is a subgroup of G. Yes? So we have, just with respect to notation, we have H as a subset of G. So if these are sets, so set notation, H is a subset of G. This, and we have H as a proper subset of G. You all remember the difference? So, go ahead.
I don't know what to prove it.
Right. So, this means that H is a subset of G, but it could also mean that G could be a subset of H. But H is a proper subset of G, means that there exists an X in G such that X is not in H. So in other words, an element here. You all follow? Good. So just as that, we have H, you all look at the notation, H is a subgrouper of G, or we could have H is a proper subgroup of G. You all follow? Same, right? Just as this. Now I'm just going to jump a bit. In a few lectures, when we introduce normal subgroups, I'm going to use N. We can say N is a normal subgroup. So it's a triangle, G, or we could have N being a normal subgroup G. So again, it's the same thing. So this one gives the opportunity for N to be equal to G, whereas this one is strictly less than. You all follow? Yeah. Perfect. Right, so definition 1.8, let G be a group and let H be a subset of G such that H dot is a group, is also a group. Then H dot is called a subgroup of G. So in other words, H dot is called a subgroup of G, or again, from before, we could just write H is a subgroup of G. Yes? Perfect. Note that the operation has to be the same. This can't be dot and this can't be some other operation. It can't be plus, right? Proposition 1.9. Let H be a non-empty subset of G, then H is a subgroup of G if the following conditions occur. So the first condition would be and identity in H, the second condition would be closure for all A, B, and H. So for all A and B and H, A, B is in H. I wrote it differently there. And the third one is inverses exist. So if A is in H, then A inverse is in H. Is there any property that we missed there? What are the four properties of the group? Associativity would be based on the operation, and the operation is the same. Everybody's okay? Nice. Definition 1.10. A subgroup H of G is said to be proper if H is a proper subset of G. So that's more or less standard, right? If H is proper, then the subgroup will be proper. Example 1.11. The following are some examples of subgroups. The group of integers is a subgroup of the group of rational numbers, real numbers, and complex numbers under addition. Makes sense, right? So, real numbers has everything, right? So, fractions, integers, everything. And integers would be z, -3, -2, -1, 0, 1, 2, 3. And R is the real, right? So R, you have to know what R is, right? Can't write down what R is, because we've never done. This is a subgroup of R. Everybody sees that, right? Nice. Under addition, remember, not multiplication, right? Because it's not a group under multiplication. Why? Because 0 does not have an inverse, yes? Nice. The group of non-zero. So here, see how we change it? The group of non-zero rational numbers, which means we remove 0 from itself, is a subgroup of the group of non-zero real numbers and non-zero complex numbers under multiplication. So in other words, we remove 0. So that will not form a group under addition because 0 is not there, and 0 is the identity for addition, but 1 is there and 1 is the identity for multiplication. And because 0 is not there, we don't have to worry about the inverse of 0, which is undefined. Therefore, that forms a group. Everybody's okay? Nice. So let's just continue in notes. I'll get back to that. Part 4, consider the collection of all 2x2 matrices that are of the form cosine alpha minus sine alpha, cosine alpha for some real number alpha. This is a group of all 2x2 matrices with non-zero determinants and a matrix multiplication. This is just extra. You could verify this by yourself. I won't go into that. It's a little bit of working, but that's just an example, which is fine. I want to get into the real meat of the matter here now. Theorem 1.12. Let G be a group and H a non-empty subset of G, such that for all A and B and H, A, B inverses in H. Then H is a subgroup of G. So this proof is important. And this is one of the rare proofs in mathematics which the order matters. Some proofs, order doesn't matter. This proof is the order matters. So if you have exactly all the steps that are in here in a wrong order, you will get it wrong. You all follow? Nice. Alright, so let's just go through this. Let G be a group. So we have a group and H is a non-empty subset of G. So you have a subset that's non-empty, such that if you have any two elements in H, then A by B inverse is in H. So in other words, we have G, we have a group, we have a next set. So G is a group, we have a set H, and we know if we have any two elements in H, then the product of A by B inverse will also be in H, yes? We know if H has this property, then we could say H is also a group. And more importantly, a subgroup of G. You all follow? Nice. We want to go through the proof. So the proof is the same standard proof. What are the four things for a group? Anybody? So let's just add 5, right? So non-empty, right? That's why I said 5. You remember the start?
Yeah.
Because I didn't read the notes, and when you do it so much, it's just ingrained because that's where students lose marks. They just go closure, blah, 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 and they forget non-empty. But it has to be non-empty, because if it's not non-empty, then it's empty, which is trivial, which just makes sense, right? Nice. So non-empty, closure, associativity, identity, and inverse. So we need to prove those 5 things, yes? Good, so let's go. Identity. Let H be an H. Then H by H inverse is an H. How did we get that line? That is a big line there. That, how?
What's that?
How? Let H be an H. Then H by H inverse is an H. Then H by H inverse is E, which is in H, where E is the identity in G. Alright, so first, right? Every single thing, this is the analysis that you need to get. Let G be a group and H a non-empty subset of G. Okay, good. You see that there? Non-empty. What does non-empty say? It have an element, yes? Good. So we have something to start with, right? So it have an element H. So let H be an H. Why H? It doesn't matter to me, right? Use P, Q, R, W, whatever. But H sounds good, right? Because the group is H, right? Don't use W and boy, well, W and H. Oh, H is H, right? Nice. Let H be an H. Everybody's okay? How did we get then H by H inverse is E? Well, we know anything by anything inverse is E, right? But how we get H by H inverse is an H? Think. So if we know that if A and B is an H, then A by B inverse is an H, yes? So if H and H is an H, then H by H inverse is an H. You follow? That's how this H inverse pop up here, because H is the same as H, which is the same as H, right? So if H and H, then H by H inverse in H. You follow that? Thief hear that? Yes. No, it's not Raj. It is understanding mathematics. Everybody's okay? Nice. So now that you see, we started with the only thing we started with was that H is non-empty, which means that H has H in it.
If H is non-empty, right?
Right.
Then the identity of parts of an H anyway. So H inverse.
No.
H inverse by default. No.
Because it didn't say H was a group. H is a set.
Okay.
You understand? This whole thing, what we're going to do now is to prove that H is a group. So we just know that there's an element. We don't know what the element is, so we take an arbitrary element, we call it H. If we have that H, then we can say, well, we have H twice. So we have H and H. Because as I said, it doesn't matter repeated elements, right? With the second H, we get, with B, we have B inverse. So H, we have H inverse, yes? Very good. But H by H inverse is E. And we know A, B is in H, therefore H by H inverse is in H, but H by H inverse is E, so therefore E is in H. Very good. Good. So we have non-empty. This was given, right? Next one is closure. Next one is associative, identity, inverse, yes? So we got identity, tick for this one. Closure, so we want to show what does closure say. Closure say if we have A and we have B, then A, B is in H, yes? So remember closure said we have A, we have B, in H we want A, B to also be in H, yes? So let H be in H. So we still have H in H, yes? Now, because we have the identity, you all look at this here? We could use the identity as A. So we have A and H is in H. So again, this is the only thing we know. We know if A and B are in H, then the product of A by B inverse is in H, yes? So now if A is E and well B is H, then what this becomes here? E by H inverse is an H, yes? But E by H inverse is H inverse, which means inverses exist. Inverse. See, it's a nasty proof. Because if you didn't do it before, then you couldn't figure it out. You understand? I mean, it's a good proof, you know? It's a good proof. So if a man trying to learn it off and you remember those steps, and he put in the wrong order X, because you can't possibly show that you get inverse if you didn't show the identity first, right? It's like growing up and trying to be 10 years before you're 9. What is that? I don't know how I don't know how this comes with it, you know. Next one. Closure, right? So we go for closure now. So that was inverse. Closure. So back here, so closure was this. So we want to take two elements and show that the product is in H. So let A and B be in H, yes? If B is in H, then because we already shown that inverses exist, B inverse is in H, yes? So now we have A and B inverse in H. Yes? So this here, we're using this now again. So we have A, and this A comes back here, and B goes to B inverse, but this is my B here. So this is B inverse is in H. And the inverse, watch it. The inverse of B inverse is B. So you get A, B is in H, which implies closure. You all see it? Therefore, H is closed under the group operation. Associativity is a property of the operation, and because H is a subset of G and the same operation is associative. Therefore, we've now proven all the properties of a group. And since H is a subset of G, then H is a subgroup of G. You all follow? Nice. So we almost did it, it's like half. We're not going to use this term as yet. We are going to use it, but it's half. So the next term 1.13, let G be a group and H a non-empty subset of G. Then H is a subgroup if and only if, in bold, for all A, B in H, A, B inverse is in H. What is the difference between this and the previous term? Both sides. There's the if and only if. You all see that? Which means we have to prove the converse part. Proof. Suppose that the condition holds, then from theorem 1.12, H is a subgroup of G. So in other words, the first part we've now proven the first part, right? So we only need to show the second part. Conversely, if H is a subgroup of G, so now we want to show that if H is a subgroup, then that property for all H, then A, B inverse, sorry, if H is a subgroup, then if A and B are in H, then A, B inverse in H. You all follow? What we've now shown, the previous term 1.12, if we have a set H and H has this property that if A and B are in H, then A by B inverse in H, then H is a group, a subgroup, yes? We've not shown that. But what we want to show now, so this implies H is a subgroup. That's the proof we now did. So what we want to do now is that if H is a subgroup, then this happens. You follow? So the first part was this implies this. Now the second part is this implies this, or this implies this. You follow? If and only if, and this is the most powerful theorem that we're going to use. So we're just dealing with the second proof. So conversely, if H is a subgroup of G, then for all A and B in H, A and B inverse will be in H. Why will B inverse be in H? Because H is a group and groups have inverses and B is an element. So the inverse of B will exist, therefore B inverse will exist. So we have A and we have B inverse existing in H, and H is a group and groups are closed. Therefore A by B inverse will also be in H. You all follow? It follows by closure that A by B inverse is in H. Yes? Anybody has any questions there? Question? It's getting a little intense. You all okay? Good, good, good. Nice. We're on page 17. Oh, look, page 18 there, boy. Right. Theorem 1.14. This theorem is the theorem you're going to use to prove something is a subgroup. You will very, very, very rarely go through all these steps for subgroup. So, by doing this theorem now, when we come to a later example, we're just going to take two elements and show that the product A and element A by the inverse of the element B, if that is in the group, then in the set, then it is a subgroup. That's the most famous theorem in subgroups. That's what you're going to use most likely all the time. Come to an example like that. Right? Theorem 1.14, and no, these theorems, you can't quote these theorems because these are my notes, right? So you're going to quote theorem. Right? You can't do that, right? Let G be. What's that? Exactly. Who is Mr. Lacan? 0. Let G be a group and H. So there are some terms that we'll come up to, like Lagrange's theorem and different things like that. And those terms are standard, famous terms, and you will quote those terms when doing questions. Yeah, like remainder theorem in maths, you're going to quote the remainder theorem, right? Pythagoras theorem, right? Nice. Right. Theorem 1.14. Let G be a group and H a finite, non-empty subset of G, such that H dot H is H. What does that mean by? Then H is a subgroup of G.
Left as an exercise.
You all understand what that means? What does H dot H mean? Y'all fear not, that is why we are here. Okay, so from this morning, 1 minus 1, I minus I, yes? This is a group, yes? Good. We call this G. We call this G group G, yes? Let's get a subset of G. So G could be this set. So normally you call the group and they say the same thing, right? So G is this set, right? But G is also this group because it's a group from this morning, right? Nice. H, let's call this H. H is this set, 1 minus 1, yes? From this morning, we showed that this is a subgroup of this, yes? You all remember that from this morning, right? And we did that by going through all the properties, yes? Non-empty, associative, identity, inverse, and closure, yes? 5 properties. Nice. Pause. Let me explain what H dot H means. So if I have an element, say a set, and the set has 1 and 2, and let's just say the operation is plus, H dot H means that I'm going to take each element in H and multiply it by all the elements in H. So in other words, H dot H, I'll replace this H with H. Y'all are trying to explain it, huh? So, okay, I'll put some quotes on it, right? So, okay, so this H, I'll take the first element in H, right? Which is 1, yes? So 1, I'll use multiply, yes? The operation is multiply. 1 multiply by H, yes? I'm going to put plus here, right? But it's just to get the idea, right? Plus the next element in H, which is 2, multiply by H, which is 1, 2. We simplify this as what? 1 by 1 is 1. 1 by 2 is 2 by 1 is 2 by 2 is, right? So let's just, so this plus union, right? Because we're dealing with sets, right? And this is what? 1, the union of two sets. 1, 2, 4, right? Yes? Which is not H. Right? You understand? Huh? But however, if we did get H, then it would mean that H is a subgroup of G. You follow? So let's try it with this. So this would be what? So H dot H would be what? 1 by H union minus 1 by H, which is 1 by 1 is 1 minus 1 union minus 1 1, which is 1 minus, is the same set, right? Which is H. So H dot H is H, which means that is a subgroup. First up, we don't need to check closure, we don't need to check identity, we don't need to check associative, we don't need to check inverse. That's it. So that's all. That's a beautiful theorem. You all follow that? That's all we need to do. All we need to do is check closure. Very, very important. Extremely important. This works for finite sets. Yeah? So you'd say since H is finite and you work out H dot H and you show you get H, therefore it's a subgroup. Yeah? Like things like these, there are main points which would be H dot H equal to H. Once you say that statement, we know which theorem you're using. Follow?
Call it a finite subgroup test.
I do not want to name anything. Finite subgroup test. What? Question mark. What finite marks test? I'll pick out after. Next theorem. Theorem 1.15. Let G be a grouper and H again, if I think finite needs to be underlined there. Finite, non-empty subset of G. Then H is a subgroup of G if and only if H dot H is H, which means H is closed. Yes? These proofs are left for your leisure. Leisure, I see. Yes, yes. So what I would suggest, spend about 2 or 3 minutes, try to figure it out, then go and Google it, because it's a simple standard proof. Understand the proof, you'll forget it by 2-3 days, and then go it over again. You follow? Nice. Determine whether, hey look, I have the example there, boy. Determine whether 1 minus 1 dot is a subgroup of 1 minus 1 I minus I. The answer is? Yes, because we know did it there, right? You'll have that remark there? Yeah. Remark. Example 2.7. Let G be a group of all real 2 by 2 matrices A, B, C, D with AD minus BC not equal to 0 under matrix multiplication. Let H, so we have a next group, H, AB 0D, which is an element of G. You all seen why it has an element of G, right? With the condition that AD not equal to 0. Verify that H is a subgroup of G. So we're going to do this in two methods. So the first one is brute force, and the second one is using the theorem. So I would actually like you all to start now, and we're going to work through this.
Do what?
Yes.
The question.
The question is meant to be done.
Awesome.
Yes. Think about it. And don't worry, you all might be a bit spaced out right now. So right now is where things start to come together. So by the end of the class, it'll be like, wow, it makes sense. Point 4.7. You see the arrow to the left hand side? Indicator arrow, yes. The end of the question says, then as is easily verified, H is a subgroup of G. We are working out that as is easily verified. So we want to show that that is a subgroup of G. So we are doing it using all the properties of H and G. So we have G, and we have H. So G has matrices A, B, C, D such that AD minus BC is not equal to 0. H is A, B, 0, D in G such that AD is not equal to 0. Right, that's the question. Show H is a subgroup. We're almost finished, only about an hour again, don't worry. But this is where things start to come together now. Where we, within the hour when we finish up class, you all would feel accomplished. Or at least I hope so. And if you all don't worry, rest assured I feel accomplished. Okay, so what's the first thing we have to prove? We're going to prove that H is a grouper, and because H is a subset of G, it'll be a subgroup of G. You all follow? So what are the 5 properties for H being a group? Non-empty. So would you all think elements, or where are A, B, and C? Where this here, A, B, and C are real numbers, right? So A, B, and C are real numbers. Yes. So we need to show non-empty. Anybody has any idea of any set that will be in H? Yes, the identity, yes. So we start now 1001 is in H, yes. Is it H? Since what is the property of being in H? We have 2 properties. Well, not properties, right? 2 conditions of something being H. The first, it must have this orientation, right? In that, this element must be 0. You are following? So this element is 0 here, so we find, and the second condition is that AD must be 0, must not be 0. Since AD 1 by 1 is equal to 1, which is not equal to 0. You all follow? Now, if you all want, you all could pay attention. Don't need to write it, because I have the solution printed there, right? Well, in my handwriting, photocopied, right? Everybody's okay with this? So just write scraps, little guidelines for working, because that's what I want. I want you all to think, hey, what do I do next? What do I do next? Figure it out. The working is inconsequential. You'll get the solution as well. So after we figured out, okay, it's non-empty. What is the next thing we need to do to show? Non-empty was the second. The next point is closed. The third point is fourth, fifth, inverse. Yes? Everybody's okay. So we've done non-empty. Closure. How do I show closure? What is the general idea for closure? General idea for closure. Closure means you have an A. Something is closed if what? From before, at the start, binary operations. A, B, in H, well, H is a set, right? Implies what? A by B is also in HS. So what do? You take two elements in HS. So let call an element in H. An element in H is of the form A1, B1, 0, D1, and A2, B2, 0, D2 in H, such that, what is the condition? Such that A1 by D1 is not equal to 0 and A2 by D2 is not equal to 0, yes? So what do we need to do now? What's that? Yes, so what do you have to do? So right now, this translate this A being my element. Remember, the element is an element of the set. In this case, our set is matrices. So a matrix in H will be this form. B is an element in H. H in this case is a matrix, so it's this form with the properties that this happens. We want to show that A by B is in H. So what is A by B? So this is my A, this is my B. I multiply them using matrix multiplication, and then I show that it is in H. So after you multiply them, you'll get, so now A, B, 0, D1 by A2, B2, 0, D2. Multiply that. What do you get? Take a minute, take a minute. got that on the board? Yeah? Right, so now that is just the expression. As far as we're concerned, that is an expression. We need to ensure that that expression, well, it's not an expression, right? It's a matrix, right? But we need to ensure that this matrix is in H. What are the two conditions that would ensure that this is in H? The two would be H. Remember, H has the elements such that entry, 0. This has to be 0. Is this 0? Yes, we're good. Yes? Nice. The next condition is that AD must be 0, non-zero. So this product by this product is non-zero. So in other words, I have to somehow prove that this multiplied by this. So I have to prove that A1, A2 by D1, D2 is not equal to 0. How am I going to prove that? You know about before from this, from here, if A1 by D1 is non-zero, which implies that A1 is non-zero and D1 is non-zero, yes? And this here implies that A2 is non-zero and D2 is non-zero. Therefore, this is non-zero, this is non-zero. Therefore, the product will also be non-zero. You all follow? Again, you'll get in the handout, right? But it's the explanation I want you all to get. The explanation and the idea of what you have to do. You work out something, you find the expression, then you relate it back to the group. You see if the properties are fulfilled. Everybody's okay with closure, yes? Now we go to subset. So we are on this second point here, point 2. When C, alright, so when C equals to 0 in G, we get elements of H. Y'all see that? G has elements A, B, C, right? If C equals to 0, then we get elements of H. So in other words, we get elements of H from G. Therefore, H is a subset of G. Right? So we just argue that H is a subset, right? Because it's a subgroup we want to argue for. It follows that multiplication is associative in H because it's associative in G. Nice. The third point, this is for identity. So A, B, 0D by 1, 0, 0, 1 is A, B, 0D, which is the same as 0, 1, 0, 1, 0, 0, 1 by A, B, C, D. Sorry, A, B, 0D. And that happens for all A, B, 0D, which means that 1, 0, 0, 1 is the identity in H. Everybody's okay? Inverse part 4, the inverse of A, B, 0D is 1 over AD. So I just had that at the end there, right? By D minus B, 0A. And when you multiply that, that is also in H because it satisfies the property that A by D is non-zero. If D by A is non-zero, then A by D is non-zero. So therefore, all elements have inverses of that form. Yeah? So this concludes the proof because we've shown all the 5 properties. Anybody has any questions? Now this is the long way. So what we're going to do now is go through the short way. The short way is using the term that we did before the AB inverse term. So I have this handout here now, which is the AB inverse term. The difference is, look at the difference here. So we're going to take 2 elements in H. We could take the same 2 elements. So we take A and B in H. And you all remember this was for closure, right? But the theorem says if you take A and a B in H and you show that A, so the theorem says if you take a A and a B in H and you can show that A by B inverses in H, then H is a group. So what we need to do is we just need to find B inverse and multiply B inverse by A, and whatever that is, show that that is in H. And that's it. We don't have to show identity, we don't have to show inverse, we don't have to show anything else. You all okay? So this is the proof here. So let A, A1, B1, 0, D1 and A2, B2, 0, D2 be in H. Everybody's with me, right? Everybody has hand, right? Nice. Remember properties because it is an H, then A1 by D1 is 0 and A2 by D2 is 0. Sorry, not equal to 0, right? And if A1 by D1 is not equal to 0, then that means that both A1 is not equal to 0 and D1 is not equal to 0, yes? So now the inverse of A2 B2 0 D2 is 1 over A2 D2 by D2 minus B0 A2. You understand how we get that, right? That's form 5 inverse of a 2 by 2 matrix. Inverse of a 2 by 2 matrix is 1 over AD minus BC, open brackets, you interchange A and D and you multiply the B element and the C element by minus 1, yes? Standard, you should know that. So now, we are multiplying A by B inverse in that line. So the also line, A is that element A, that matrix A, by B inverse is which we now found there. So I forgot the 1 over AD there, right? So it's squeezed in the middle, right? Chukatine. In the second line, I pull it out and I made it look nice. I expanded those two brackets there. I multiplied them, sorry. I simplified and I got my last line. So I have my last equal sign there in the middle of the page is 1 over A2 D2 multiplied by, in brackets, and the matrix is A1 D2, A2 B1 minus B2 A1, 0, A2 D2, yes? Now we need to show, the only thing we left to do now is to show that that is an H, yes? Remember the two conditions for it to be an H is that that third element there must be 0, which happens. And the other property is that when you multiply the first element by the fourth element, that product must be non-zero. Now since A1 is not equal to 0 and A2 is not equal to 0 and D1 is not equal to 0 and D2 is not equal to 0, we know that from before because at the start at the top, because they are in H, then obviously the product of that cannot be equal to 0. Yes? Hence, we've now shown that that is an H. And then you conclude, remember that 1 over, after the hence 1 over A2 D2 by that matrix there is an H, but that is actually my A1 B1 0 D1 and the inverse of A2 B2 0 D2. Therefore, you've shown that A by B inverse is an H. Hence, is a subgroup of G. You follow? And this is much simpler, yes? Much more, that's why it's beautiful. The only thing that could have made this better was a colored paper. Anybody has any questions? So, that is a huge learning point. That this theorem is, you need, by the end, we have not finished this yet, right? But we need to pause and understand that you all understand what a group is, yes? You all understand what a subgroup is, right? You understand the subgroup test. We could call this the subgroup test, yes? The theorem to prove that something is a subgroup from a group is the AB inverse test. Good. That's 3 of the biggest learning points today. We're moving on. Let H be the group in example 2.4 and let K be this new set 1B0 1. Then K is a subgroup of H. So on your own time you could prove that K is a subgroup of H. You follow? And what's even better, you could prove it's a subgroup of G. You understand that? But you understand how to prove that K is a subgroup of H, right? You take two elements in K and show that when you A by the inverse of that element will be also in K, yes? And that's it there. And you have to show non-empty as well, right? Good. So that's exercise, that's leisure. Let G be a group of all non-zero matrix numbers A plus IB, comma, A, B, real, blah, blah, blah. Under multiplication, and let H, so H is defined by that there, verify that H is a subgroup of G. Leisure. Leisure. No, because we did one example and we did a good example. You follow what's going on? And I highly recommend that you all do it. Take like a minute or so. Okay, like 5 minutes. Okay, probably 10.
Is it Googleable?
Nah. You have an example, just follow the example, right? Take 10 minutes. I will be here tomorrow recording. Most likely. Let G be the set of all 2 by 2 matrices A, B, C, D, where A, B, C, and D are real numbers such that A, D minus B, C is 1. This one is different. Define the operation dot in G, so it's normal metric multiplication, as we did example 2.2.6 via multiplication. We leave it to the reader to verify that G is also a group. In fact, an infinite non-abelian group. You all know what's going on there, right? Leisure. I know there's about 4 or 5 of them, right? Just choose 1 or 2. I just choose 1 or 2. What I would do, I would go back over the example in the handout that I gave, do it by itself, and then check it, and then tackle one other example, yes? Nice, so we've covered all these handouts here now. I believe so, yes. Well done, Rajesh, well done. Now we are going to finish off these notes. We are on example page 18, lemma 1.18. Lemma 1.18. Let H and K be subgroups of G. Then H intersect K is also a subgroup. Yeah? We could prove this? What are y'all thinking? Are you seeing it in your head, right? Come, let's just do it. I could finish this in 10 minutes. 10, y'all, 10. Just T-E-N. 10. 10. 10. Yeah, don't look at it. Alright, y'all. So we have G. Y'all, again, we really don't want to represent on diagrams, but what we do, right? We have G and we have H and we have K, and we want to prove that this here is also a group. So what do? We want to prove this is a subgroup of G, right? That's the question. So what do we want to use? Method would be what we now did. Anybody? A, P inverse. Yes? You understand that, right? Beautiful. My God. So what's the format? For this to work, where do these things come from? What happens here? We need an A and we need a B in where? In H intersect K, yes? And then we have to do some working and show that this happens, yes? Nice. You need a little walkthrough, yes. I mean, we now just spend last hour. You know? I think you know it. So, what we would need to do is, first we need to show that it's non-empty, yes? So we need to find some random element that is in the intersection of both of them. So, what element, the answer is in the book, so I'm just walking you all through the proof, right? You'll have the answer in the notes. What element would be common to both H and K? The identity, yes? Why? Because both of them are groups, yes? Since H is a group, since H and K are groups, the identity is in H and the identity is in K. Therefore, the identity is in the intersection. You follow? Hence, H intersect K is non-empty. You follow? You understand, right? Don't just full stop there, no. You have to finish off by saying it is non-empty, yes? Good. So the next thing we need to take two elements in the intersection. We have no idea what the elements are, so we just randomly take two elements, yes? Just as in our questions, we will take a A and a B and H, and how does A and a B look? A was our matrix, so we make up the matrix A1, B1, C1, D1, and we take a B, which is our A1, A2, B2, C2, D2. You all follow? So we say let, what you all want to call it? X and Y be in H intersect K, yes? This is just a sketch, right? You'll have the proper thing. Just to understand, right? Which implies that X is in, which implies that X and y, blah, 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 blah. I'm just thinking of the format, that's all, sorry. Ultimate baby steps, right? Which implies that x and y is in H, also x and y is in K. Yes? Yes? Yes. Since y is in H and H is a group, what that means? Y inverse is in H. You okay? I guess we're going in this line. Since y is in K and K is a group, y inverse is in K. You all follow? Which implies that x by y inverse is in H. Why? Because it's closed, right? H is a group and H is closed, right? Yes? Here, which implies that x by y inverse is in Ky closure. Therefore, x by y inverse is in H intersect K. This line here was irrelevant, right? I didn't need this, right? Sorry. You all understand? So just to get the idea, you know, extract everything you have from the question. Anything they give you, you just take it and start and go with it. Right. So now we are on cyclic groups. So all of this has self-study. I just want to introduce the idea very quickly, and then we'll go on. So definition 1.9, a group G is called cyclic if there exists an element G in G such that G, such that G equals to G to the N such that N is in Z. And G equals to G dot G dot G dot 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 G N times, if N is greater than 0 or it's equal to E, if N equals to 0, or it's G inverse by G inverse N times mod N times, my bad, sorry, if N is less than 0. The element G, so y'all, this is important, this is very important. So the element G, the element that gives all the other elements in the group, is called the generator of the group. Makes sense because it generates the group. Yes? Lovely. So, can anyone think of a cyclic group? Yes? Well done. So we have G. It's 1 minus 1, I minus I. This is a cyclic group. What is the generator of this group then? Minus I. So minus I to the 1 is minus I. Minus I squared is I squared, which is minus 1, yes. Minus I cubed is I. Just multiply this by I, that's all you're doing. Just look at the last one, multiply by I. And minus I cubed, 4, yes, well done, would be I by minus I, which is minus I squared, which is 1. You all follow? And then minus I to the 5 would just give me back I. So it just repeats. It repeats. You all follow? So the generator in this case is minus I. Do we have any other generators?
I.
What's up?
I will get generator.
That. we have another generator of I as well. So I to the 1 is I squared is minus 1, I cubed is minus I, and I to the 4th is 1, yes. You follow? So it is possible for a group that is cyclic to have more than one generators. Lovely. Remark: if a finite group G can be generated from one of its elements G together with its G inverse, then can be generated from G only. So I'll just leave that for you all to go through. Example 2.2.1, the following are examples of cyclic groups. So the group Z of integers on the addition is a cyclic group generated by 1. So we have Z, and we say that Z is generated by G on the addition. So in other words, 1 to the 1 is 1. 1 squared, remember our table here is G by G, but the operation is addition. So it's really 1 plus 1, which is 2. 1 cubed is really 1 plus 1 plus 1, which is 3. You all follow? And so on. So this shows that we can have cyclic groups that are infinite as well. Yeah? Lovely. Definition 1.22. The order of an element G is the smallest positive integer n such that G to the n equals to E. The identity in G, if such an n exists. Otherwise, G is said to have infinite order. So, the order of minus 1 would be, as I said, 4. The order of I would be 4 because it gives you back the identity. Yeah? Proposition 1.23, cyclic groups are abelian. I will leave that for you all to go through. Yes. And the rest of the chapter, which are just 2 pages, the proofs are a bit interesting, I may say. So I wouldn't spend too much time right now in this mini study group because I want to get on to some other topics in other classes. So I'll leave this for you all to go through. If not now, during the semester when it starts, please review the notes, come back. It's complete. So anybody has any question? So with that, I'd like to thank you all for your attention today on the first study group. I think it went excellently. So I look forward to seeing you all tomorrow. And please make sure, if it's one thing you all need to do before the study group finishes, is write the exam. Yes, you need to solidify your learning with an attempt of the exam. And it's going to be a nice exam, you know. It's just going to give you confidence. So with that, I'd like to thank you all. Enjoy the rest of the day and look forward to seeing you all tomorrow. Enjoy. Bye.